Hi, everybody. It's Mr. Neff. Let's look at some of these vectors homework problems. On number 8, it says a road that rises 1 foot for every 100 feet traveled horizontally is said to have a 1% grade. Now, here's a road in Idaho that has a 6% grade. So that means it's going to go up 6 feet for every 100 feet traveled. So if we go 100 feet like this, let's say that's 100. Obviously, this isn't going to be drawn to scale. It's going to go up 6 feet. That's, again, not to scale. It says at what angle is this road inclined above the horizontal? So we're looking for this angle down here. Now, compared to that angle, this is the adjacent side, and this is the opposite side. So I'm going to use tangent on this, and so I'm going to say tangent of that unknown angle is going to be equal to the opposite side, 6 feet, over the adjacent side, 100 feet. So now I'm going to do an inverse tan of both sides of this. And so inverse tan here is going to undo the tangent. Just leave me with theta. But what you do to the one side, you must do to the other side. 6 over 100, feet canceled. And inverse tan of 6 over 100 is going to be 3.4 degrees, which doesn't sound like a lot, but you'd think this was a pretty steep road. Number 17 says the displacement vector from your house to the library is 760 meters long, pointing 35 degrees north of east. So from your house, so let's say this is your house, to the library, 35 north of east. So east, of course, is here. 35 degrees north of east would be something like that. Let's say this is it. Here's where the library is. So I put 35 degrees on the north side of east as opposed to the south side of east. So they want to know what the components look like. So I'm going to draw in this component here going straight east. And notice how far I drew that. I drew it till it was right below the end there. And then I'm going to draw the other component straight up like that, the north part. Now, you might be tempted to draw this over here, and that's okay too. Either one of those is just fine. I'm going to leave this here so it forms that nice triangle, and it's easy to see what to do trig-wise. So a two-dimensional displacement, I like to call delta r, and so I'll call this you might say delta rx, but the displacement's the one funny one that you usually just call that delta x. And you could call this delta ry, but again, most of the time that's just called delta y. So how big are those? So let's say the delta x, find the delta x. That's the adjacent side to the 35. The delta r is the hypotenuse. And so we're going to use cosine for that. So cosine of 35 is equal to delta x over 760. I didn't write that down here, but this delta r is 760 meters in magnitude. So it's 760 meters. So 760 meters cosine of 35 degrees is what I have for the delta x. And when you run that through the calculator, you end up getting a delta x of 622.5, lots of fives. And I'm going to round that just to two significant figures, 620 meters for the delta x. Now, the delta y is the opposite side to 35, so I'm going to use sine for that. Sine of 35 degrees, delta y over 760, so 760 meter sine of 35 degrees is delta y. And from the calculator, I'm going to get 435.918. Let's round that to two significant figures, 440 meters. Before I go off of this one, I'll have you notice something, that these two lines are real similar to each other. In both cases, I used the original magnitude of the vector, the 760, times either the sine or the cosine of the angle. And you're always going to notice that pattern. When you're finding components, one component uses the cosine and the other component uses the sine, but otherwise it's exactly the same calculation. The one that uses the cosine is going to be the one that's right beside the angle. So the 35 was here, and so the component that used the cosine is the component that is the adjacent, and so it's the one that's going to be right beside. As opposed to, the other component is going to use the sine. And so you see that in this case, the delta Ry or the delta y was the opposite side, and so it used the sine to get it. So maybe that's a way that you can jump to the calculation of the component really quickly. Maybe you can say, hey, I know it's going to be original magnitude. Here it was 760 times the sine or cosine of the angle. The cosine one is going to be the one that's touching the angle, the adjacent, and the sine is going to be for the one that's not touching the angle.